on the orbit of the Earth, parallax measurement. Here is the sun, here is Earth. We set up a little bit of triangulation that looks something like that. This is a distant, this is a star. And what we treat this as is an arc length. So this is 1 AU. This is a distance here to the star. And we will say that the parallax angle, I'm going to call that phi. And the parallax angle is going to be given by what? The ratio of what two distances? The arc length divided by the radius. Okay. So what does that say the distance to the star is going to be? Yeah, that's going to be given by 1 AU over this angle, parallax angle measuring what unit? It's got to be radians, right? So what do they tell us in problem 1? They say that we have measured the parallax for a star, and we've measured this at 0.00029 degrees. How far away is the star? So we can take this expression right here. I can write my 1 AU here. Can I put my 0.00029 in here? Not yet.
It's not radians.
It's not a radians yet. So let's get it converted. How are we going to get it converted into radians? 180 degrees will be pi radians. And what that does is, I ended up with 5.06 10 to the minus 6 radians. So let me write that in. 5.06 10 to the minus 6 radians. And remember, radians don't have any units to them. So the radians just drop out. And I'm going to be left with a distance in terms of AU. And I got an answer of 198,000 AU. Now for stars, we usually don't use AU. What would we use instead? Light years. And the conversion there is 1 light year is 63,000 AU. And that's a pretty good conversion. That's accurate to better than 2 sig figs, I think. So that's a handy conversion. That's one that I put that in my notes. A light year, 63,000 AU. It's going to make these calculations go really fast. That worked out to be how many light years? And I got 3.14 light years. What's wrong with our answer? What's the closest star to Earth? It's farther than that. It's 4.3. So Alpha Centauri is actually, so they gave us a parallax angle for a star that doesn't exist, first of all. There is nothing that close. So all the stars in reality are going to have parallax angles smaller than this. Anyway, that's how you do this, right? If I get a parallax angle, I can get a measurement out to a distance to a star. All right.
Questions on that?
Let's look at 15. So, '15 is a type 3 problem, so I guess you got to be really careful on this one. I don't think it's not really a type 3, they just put that in there. Okay, in problem 15, we have 2 different stars. I'm just going to call them star 1 and star 2. And they give us a bunch of information about these stars. So, star 1, star number 2, So I'm observing these two stars, you know, that one there and this one here. And one has a wavelength that peaks at 470. So let me write that in, peak wavelength. And the peak wavelengths are at 470. What color is that star? That's a blue star, yeah. And the other one peaks at 720.
That's red.
Yeah, that one's red or infrared, really. But what we would see is that would be a red star, and that'd be a blue star. Okay, here is the HR diagram. Where's red and blue on the HR diagram?
Blue is the bottom.
This axis is what? This is surface temperature. And remember they did surface temperature backwards. So that means that this is the red end and this is the blue. So we got a couple possibilities here. If these are main sequence stars, then where is my star located? Where is this star located on my HR diagram? Yeah, it's over here somewhere, right? That's what I'm guessing. Where would the red star be located? Yeah, it could be down here. Now, there's another region of stars here. There's the red giants. So it could show up in either of these locations. Let's see if they give us any more information. Now, what I did was I took the peak wavelength and I used that to get a temperature for the surface. So I went ahead and plugged the 470 and the 720 into this formula, and I got surface temperatures of 6170 nanometers, and that's not really too blue, is it? Actually, that's not that much higher temperature than the sun. It's actually pretty close. And I'm writing nanometers, which makes, of course, no sense.
Yeah, it's Kelvin.
These are kelvins, yeah, definitely kelvins. Sorry about that.
So there's no millimeters, 2.9 millimeters?
Yeah, so the constant here, if we're using,
Divided by nanometers?
what law is this? This is like
okay.
Stefan Boltzmann. So what we've got is,
Do we convert that millimeters to nanometers?
yeah, or you can do this. You can say temperature times peak wavelength is 2.9 million nanometer kelvins. That works. So I could put the 2.9 million in here, divide through by the 470. That will give me a temperature in kelvins. And that's how I filled in that table right there. And then they say in terms of apparent brightness, one of these stars is brighter than the other by a certain factor. So, and it's actually 11 to 1. So it says that, I guess this is being called brightness. Now, brightness is actually intensity measured from Earth. So I'm standing on Earth and seeing how intense the starlight is from these two stars. So that's got a distance effect built into the numbers. And this worked out to be in a ratio of 1 to 11. They did not give me numbers for the intensity. I would have rather just had numbers given to me. Instead, they gave me a ratio. So the ratio here is intensity 2 relative to intensity 1 is a factor of 11. So let's think about that. Now we've got questions going on in terms of brightness. How do I get brightness converted into luminosity? Because that's what I really want to be able to compare these stars. I want to know what the luminosity is. And they don't give us something to tell distance. You know, if they told me parallax, I could calculate distance. But instead what they say is these two stars appear to be part of the same star cluster. So it says that they're the same distance from us. So these are two stars in a star cluster, a group of thousands or millions of stars that are all kind of in the same region of space. And we imagine they all formed roughly the same time, and they're roughly the same distance from us. So if I've got a ratio of brightness that's 11 to 1, and these two stars are the same distance from me, what's the ratio for luminosity? And that would also be 11 to 1. Okay. And the key here is that they told me these are the same distance. Okay, let's write that out and see what that would look like. So the brightness or the intensity from star number 1 would be equal to the luminosity of star number 1 divided by 4 pi distance squared. And what would be the intensity of light from star number 2? Will be the same formula, right? So we can take the luminosity of star number 2 divided by 4 pi d squared. Since the distances to the two stars are the same, the ratio of luminosities will match the ratio of intensities. Okay, we have to rethink things now because, let's see, we had star 1 that was kind of in this region here, maybe, main sequence. What do we know now about the luminosity of star 2? It's higher. So is star number 2 a main sequence star? Is star number 2 down here? It's up here. So this is starting to look like, I'm going to guess this is a red giant. And I'm going to guess this is a main sequence. That's what it's starting to look like. And the red giants are going to be here somewhere. What's on our vertical axis here? This is luminosity. All right. Now, what is it they want us to actually, what is it we're solving for here?
Size.
Oh, the diameter. We want to find out what diameters are like. So again, we're going to be stuck with ratios here, right? They didn't give us enough information to go in and just flat out calculate a diameter, but we can work from ratios. So what we'll do is we'll use some more ratio stuff. What I'm going to say is that the luminosity for either one of these stars is going to depend on surface intensity times surface area. So this is something we talked about on Thursday. Luminosity, surface temperature, and radius of the star have to follow this formula. So I'll just write it down for each one of the stars. So I'll write this down as luminosity for star number 2 is proportional to its surface temperature to the 4th power, and its radius or diameter to the squared power. What should we do for star number 1? Well, that's going to have the same form to it. Sigma t to the 4th, 4 pi r1 squared. And then to turn this into a ratio problem, what do? We divide. Yeah, so we're going to divide here, and we're going to divide here. And it says that L2 over L1 is equal to T2 over T1 to the 4th, and R2 over R1 squared. And we are solving for R2 over R1. So that's going to give us R2 over R1 squared is L2 over L1. And then we got to make sure we get this inverted, something like that. And I can start putting numbers in. How does L2 compare with L1? How do the two luminosities compare? Yeah, L2 was larger by a factor of 11. Okay, so for that one, we will put in 11 to 1. And how did the temperatures compare? And here we're going to put in 6170 divided by 4028. And that is going to pick up a factor of 4. Power of 4, sorry. So R2 over R1, I ended up with a factor of I got a factor of 7.78. So about a factor of 8, but 7.78 in particular. That's the ratio of ratios. What's the ratio of diameters? Same thing, right? So that does look like it's a red giant. It's not an extreme red giant, but it does have a diameter that's 8 times the diameter of the star that's over here. So star 1 is here, probably, and star 2 is over here. And that's going to give us like a power of 10 in terms of luminosity, and it's going to make this star kind of bluish, and it's going to make the other star very red from surface temperature effects.
So the last column is the ratio.
The last column?
What's there? What is it? Tell me.
I wrote too many columns. Sorry about that.
It's a clue.
It was a space holder.
When are the,
Yeah.
since we're done with this problem, when are the lab from last week?
When are the labs due?
Because
Labs are due
before the weekend thing is your rule.
next week, Thursday.
The previous,
Yeah.
the
So I want all the lab. I would like to have all the labs in by the last day of instruction. And for us, that's next Thursday.
so it's okay to do that.
Yeah, get them in then. If you bring them into the final, I will frown. I'll probably still take them, but who knows what's going to happen to the lab reports that comes in with the final. So just to play it safe, get all the lab reports in by next week on Thursday. Okay.
I'm not gonna have no Jason paper shredder.
Yeah, that's right.
Into
Paper shredder next to
round
Nate.
shred.
Yeah, that's the plan. All right. Any other questions on this example? No. All right, let's move on. See what else we find here. I do want to look at one of these fusion. We have some different fusion reactions we can look at, right?
I have another random question. I kind of
Yeah,
forgot.
okay.
Uh,
Yeah.
The final is like evenly distributed between all the chapters.
As any final exam should be, right? And that's kind of the reason for our fourth midterm is by the time we've taken the fourth midterm, then we've taken a midterm on everything that we've done in the course. And so the final gets to be evenly distributed. So you can kind of count on roughly 2 problems from each portion of the course. But of course, there are problems now that could draw on different ideas from different parts of the course. But that's basically the idea as I look in the first 4 chapters and I try and find 2 problems related to those, and I look at the next 3 chapters and find a couple of problems there. Okay. All right. We should look at this expansion of space stuff too. So let me take a look at 25. '25 says, estimate how much of a wave shift you would get in a hydrogen spectral line from a galaxy that is a certain distance away from us. Now here we had developed, this is an expansion of space problem, and on Thursday we had developed our own set of formulas for this that are more general than the ones in the book. The ones in the book work well out to, I don't know, tens of millions of light years, but we want to be able to do billions of light years. Let's face it, we want to do really large separations. how much redshift will there be, and at what rate would these galaxies be separated due to the expansion of space. So let's try using the formulas, I guess, from class. I'm going to use those. Remember, this is an expansion of space problem. It's very important that after you leave this class, are galaxies rushing through space? Because that's what you read about all the time. The galaxies are just rushing through space, and that's not true. The galaxies are just kind of drifting ever so slightly through space. Why is it then that the distance between the galaxies is increasing? Space is expanding and the galaxies are just getting carried along for the ride. Okay? They're just getting carried away from each other due to the expansion of space itself. So in 25, we may have to rephrase some of this too. No, I think we're good. The phrasing and the problem all seems fine. All right, in part, I'm going to do another table, I guess. So what they do is they say there is a galaxy a certain distance away from us. All right, 7.0, big M, little c, YR stands for what?
Year.
7 million light years away, so that's the distance. And then they do 70 million light years. And we just kind of smiled at those numbers because a galaxy that is 7 million light years away is like one of the very closest galaxies to us. This is not an extreme number at all. Even 70, that's just the local neighborhood galaxies, right? That's not very far away. Well, they're asking how much of a redshift we would see for a galaxy that was this far away. And we have an expansion rate for space. So we're going to say the galaxies are this far away, which really means how much time did it take for the light to reach us from those galaxies. Let me get these units right. So when we say a galaxy is 7 million light years away, we really mean this. We really mean it took 7 million years for the light to get here. Okay? And same thing for the 70 million light year galaxy. It took 70 million years for the light to reach us from that galaxy. And from that, we can come up with a redshift. And the formulas we worked from here were the redshift. We've got to get our universal timeline here. All right, t equals 0 is what? Big Bang phase of the universe. And where did the Big Bang happen? Everywhere throughout the entire universe. Big Bang did not happen in one location and then all the material spreading out. The Big Bang happened everywhere. It was just that phase that the entire universe went through. And now what we've got is we've got two galaxies, or two regions of space. This is region A, this is region B, and following after the Big Bang, these two regions of space are separating away from each other, and at some point galaxies formed, right, from the material in those regions. So after a while we can say trajectory A and trajectory B refer to two distinct galaxies that form and are separating at whatever rate those regions of space are separating. Okay, so that's what this looks like. And then we introduced some ideas of, we said T0 is the time at which the light leaves galaxy A. Here is some light that is given off by galaxy A, and some of it is pointed towards galaxy B. and we can follow that light back to where galaxy B receives the light. And we said at the time the light leaves, we're going to call that T naught. The time that the light arrives is going to be TH, where TH is what? It's the Hubble time. And what is the value for TH? What's our best measured value for this? 13.7 billion years. Which is a good number because 13 and 7 are both prime. Prime numbers are always both. So in the book, they do this in terms of something called the Hubble constant. The Hubble constant is 1 over the Hubble time. It's just they're working in terms of the inverse. I kind of like the Hubble time because I have a better feel for what 13.7 billion years means to me. That's a certain amount of time that feels more familiar. So yeah, rather than 1 over 13, 1 per 13.7 billion years. So anyway, that's what TH is. And then what we said was, at the time the light left galaxy A, the two galaxies were separated by a distance. Distance of separation. And the x naught would be equal to v t naught, where v is the rate at which those regions of space have been separating since the Big Bang. Now, our model assumes that v is just a fixed constant value. It's not quite true. You can go back and show, using redshift over the past 12 billion years, that there was a more rapid rate and then it slowed down and now it's picking up again. So it's a little bit of a curvy line, but it turns out assuming a straight line works really well as an estimate. So that's what we're going to do. And it gives us some kind of easy to conceptualize formulas, which is a nice feature. So this is the kind of stuff that we can write down. Here's x naught, here's how far they're separated now. Speed, we said, was c times the ln of the redshift. So we've got all these, and then the redshift can be measured in terms of wavelengths, or it can be measured in terms of distance of separation, or it can be measured in terms of the ratio of how much time has passed since the Big Bang up until light departs and light arrives. So any of those ratios will give us a redshift. All right, what do we have to work with in this problem? What's t? Yeah, t is between here and here. T is the amount of time that the light had to travel to reach us. So if we look at t, t is actually equal to th minus t naught. Well, what we could do in the problem then is, well, we could do this first. What's t naught? You go, well, t naught would be equal to th minus t. That would be 13.7 billion years. And then what is t equal to? Minus 7 million years. Okay, what's 13.7 billion minus 7 million? It is 13.7 billion. Okay, so you can see on the cosmic scale, the textbook is being really cautious. They're picking some really low numbers. But anyway, that's another example of that. So what we can do is this. We can get the redshift this way. I can say the redshift is equal to th, which I already know. And then the t naught, I can get from here, sort of. I'm going to get this as th over th minus t. So I did that. I ran the numbers on the redshift. And for the redshift on galaxy number 1, I got a redshift of 1.00050. And for galaxy 2, I got 1.00503. So that's how much of a redshift we are expecting to get. So if I take a look at the wavelengths, if I have this much of a redshift, these guys right here. What's the wavelength that we will observe for this hydrogen light? You say, well, the wavelength we observe is going to equal the wavelength that the light started out with, times what? Times that redshift ratio. So it's going to be this times the redshift. And they tell us that theta naught is equal to what? Theta naught, they say, is the 656 line in hydrogen. All right, so the light leaves at 656 nanometers. What do we observe this at? And it comes back, or we pick it up at 656.33 for the first galaxy and 659.3 for the second galaxy. And that says that we need one more column. Oh, that's what that extra column was from before. It was actually part of this problem. So we can do a delta lambda. This comes in at 0.33 nanometers, and this one comes in at 3.3 nanometers, and that's not very impressive. I want a big redshift. I don't want a little fraction of an nanometer. But that's what they gave us. Can I really get away with this in terms of significant figures? What are we assuming about the wavelength here? Kind of. We're kind of assuming that this is 656.000. Now, we don't have to actually make that assumption. What we can do is we can write this as a difference. So these numbers are still good. Even if this is only known plus or minus a nanometer, these numbers are still going to be good. Okay, so the delta lambdas are still going to work out. These are the numbers that are suspect. We don't know if those are exactly what we wrote down. All right, let's try a different value on these. I want to try one that is, what if instead of 70 million, what if we do 10 billion light years? And yeah, anything that's on the midterm or the final is going to be billions of years. Because that's where you can really see the redshift. So after 10, if we're looking at a galaxy 10 billion light years away, how long has the light been traveling? 10 billion years. That's our definition. Where is T naught going to be? Well, kind of where we placed it, maybe about here. Because this whole length is how far? That's my 13.7. And we're looking 10 billion years into the past. That's going to put us at 3.7 for T naught, right? So again, we're going to have TH 13.7 billion years. T naught is going to be going back 10 billion years. That'll put us at 3.7 billion years. And we get a redshift from that. What's the redshift going to be this time? And I got 3.5, but I think it's because I used the wrong numbers. Why did I use 14? I used 14.0 instead of 13.7, which is
minus 10.
Why did I round? I should not have rounded. What do you guys get on this? If you do 13.7 divided by 3.7, what does that give us? 13.7, 3.7, what's going to be?
3.70.
Oh, 3.70. So we're going to get a redshift of 3.70. What is that wavelength going to arrive as in terms of wavelength? I've got this 656 nanometer wavelength. It's going to get redshifted by 3.7. What wavelength will it come in at?
2429.
Okay. Now that's a redshift, right? That's one you can see something really happen. It's not even the visible part of the spectrum anymore, right? It's off in the infrared. I got to look in the infrared for it to pick up this redshift on this line. And I'm not even going to bother with delta lambda because I can already see. Yeah, it's huge, right? So we went from here to here. Okay. And those are some of the most distant things we've measured. I think the most distant galaxies are coming in at like 12 billion light years, something like that. Those are really distant objects. And they got to be pretty bright for us to pick them up. These are very luminous galaxies. Things like quasars, if you've heard of quasars. Or if you have a microwave oven, it's made by quasars. All right, questions on that? Anything on galactic separations? So you guys, again, go ahead and put this into your notes. You're welcome to use these. We never actually fully derived this one, but we're going to go ahead and use it. And again, what this will do is it will match up with the book for tens of millions of light years, hundreds of, but it will maintain accuracy all the way back to 10 or 12 billion light years, which is a nice feature. Yeah.
So that speed is solving for how fast those space
How fast they're, yeah, let's do that. We didn't calculate that. That's a good idea. So let's calculate that. At what rate are these two galaxies separating? And that just comes down to what? What's the ln of r? Right, what's the ln of 3.7? Okay, so that's going to be 1.31 times c. Uh-oh, is that a problem?
No.
It would be a problem if we were back in special relativity, or not. We're into general relativity, and that says that the speed limit of c, that's just for local measurements of c. But if I have a region where space is expanding, and I look at far enough distances, I'm always going to find objects that are separating faster than c, so it's not a concern. This is one of those questions that penalizes good students, right? Because good students stop and they think, oh wait, it can't be going faster than c. But you have to go beyond that and say, yeah, general relativity now, it's fine. It can be bigger than c, not an issue.
Then you're a good student.
Yeah, that's right. The good students get them. The not really so good students get it, and then the good students get penalized. Right. So pick one direction or the other in preparation for the final. Either go with the good approach, or go with the not really clear what's going on approach. Either of those works on this problem. All right. What else do you guys need to know for the upcoming exams?
You said fusion. You mentioned fusion.
Yeah, let's look at a fusion. That's a good idea. Let's look at. Yeah, 31. You guys are good on 27. You're good on 31. $35 we're not really worried about. Don't. That's kind of a rough pattern of numbers on 35. But 49 definitely we want to take a look at.
And what chapter?
We're still in 44. This is everything right now in 44.
So 35.
Yeah, is that a sign?
35 is, yeah.
35 is. Yeah, 35, don't worry about having so much. Yeah, but 49 and 57 we may take a look at. 57's a little bit out there. There's a lot going on in that last problem, in the last chapter of the last semester of physics. As there should be. Okay, since the Big Bang, where has fusion taken place? There's really only two sources for all the different elements that we see in the periodic table, because the universe just started with a bunch of protons, electrons, and neutrons, right? So where did all the fusion take place that built up all the elements in the periodic table? Big Bang, stars. Okay, that's pretty much it. So the Big Bang fused which elements into which elements? Hydrogen, helium, that's about it. There's little bits of traces of lithium and beryllium. That's about it. Okay, not much from the Big Bang as far as getting through the periodic table. The rest of the elements came from where? pretty much, yeah, higher mass stars, and in particular the highest mass stars.
The red giant.
Neutron stars?
Yeah, even beyond, yeah, so the ones that go all the way to supernova. The ones that either become neutron stars or black holes. And those stars are able to fuse all the way up to iron, and then they blow themselves up. And during that last phase of the supernova explosion, they generate all the elements of the periodic table, scatter it out into the galaxy. That enables what? It enables solar systems like ours to form. Okay, so we've got Thanksgiving coming up here. I don't know what your Thanksgiving traditions are, but I'm always sitting around a table where people go, let's go around and all say what we're thankful for.
Sure, you're a real interesting guest to the dinner table.
That's right.
man.
So here's a good way not to get invited back. Is when it's your turn, say, I'm thankful for high mass stars. Which seems like the most obvious answer to me. It just kind of enabled everything, right?
Yes.
Anyway, try it, see if it works. I haven't had much luck with it. I tried it a second time. You said this last year. You went through this last year. No more of that. But everybody else gets to come up with these lame things that they're thankful for, right?
I'll try it this
So
year.
try it.
I'll give it
Yeah,
a try.
take a
Give you some
shot.
feedback next week.
See, yeah, perfect. Let me know how that goes. All right, let's take a look at problem 49, because this is something we're thankful for, and we are thankful for magnesium, right? I'm thankful for, you guys thankful for magnesium?
Sure.
Yeah,
It's
right?
natural light.
It's part of, yeah, it's part of the earth. It's in photosynthesis, right? All plants have magnesium in their photocenters. All right, so the reaction we have here is an example of a nucleosynthesis reaction. And the reaction we have is taking a couple of carbon 12s. Where did the carbon 12s come from? Well, they came from fusion of helium, and the helium came from fusion of hydrogen, right? So it's a series of steps. Now we're all the way up to carbon, and once the core hits high enough temperatures, two carbons can fuse and form a magnesium. Okay, plus you got to get photons because you have to have something that can carry off all that energy. It's all the kinetic energy that gets released, right? So that's our nucleosynthesis process. And then they just have us go through and kind of ask questions about how much energy is released in this reaction. That sounds like they're asking Q, right? So how would we do Q for this reaction? I want to take the mass of what? 2 carbons. So we'll take 2 carbon masses and subtract off the mass of the magnesium. Where am I going to get those masses? Periodic table or Appendix F? Appendix F, right? Okay. So we got to get the right isotopes on these. And I looked these up, and you guys are required to know the mass of carbon 12. It's what?
12.
Well, 12.0000000. Right, that's our definition. So the definition of the kilograms in there somewhere, right? And Avogadro's number. This is really a fundamental starting place for us now.
Did you actually count the number of zeros you put there, or?
No, I was going to put a line over at the end anyway, so it didn't matter. I just figured in Appendix F, these things are known to 9 digits past, so I just put 9 in to match Appendix F. But, and then the magnesium. Actually, I don't have 9, do I? I was thinking 9, but I don't think I have it on these others. The magnesium here is 23.985042. These are in atomic mass units, so I ran the numbers. Is this charge balanced? Yes, it is charge balanced. And I know it's going to be charge balanced because it's just conserving protons and neutrons. The number of protons going in matches the number of protons coming out. The number of neutrons going in matches the number of neutrons going out. There are no electrons and neutrino stuff going on. It's going to be charge balanced. So I just looked up the neutral masses for all of these, and the electrons will cancel out automatically. And we'll be left with a Q value of 0.014958 atomic mass units, which gives me 13.93 MeV. That's not bad. That's a pretty good amount of energy still being released in fusion, even though we're a fair ways into the periodic table now, right? So that's a good energy release. And what does it say in part B? B says how much kinetic energy would each carbon nucleus need to have in a head-on collision if fusion is going to occur. And remember, this is the idea of the nuclei will just touch. Okay. So here is one of my carbons. Here is my carbon-12 nucleus here. Here is my carbon-12 nucleus here. We're going to have this come in with a certain amount of kinetic energy. This one's going to come in with a certain amount of kinetic energy. Why did we have them come in opposite directions with the same amount of kinetic energy? What's the reason for setting it? Why don't we have one carbon sitting here and another one come in and hit it?
Simpler equation.
Because that would be harder,
Yeah,
okay, to do, because this automatically conserves what? Momentum, exactly. So this automatically takes care of momentum conservation. If I have the two objects come from opposite directions, same speed, then momentum's taken care of. And that means any energy that gets released is going to be going into additional mass, or it's going to be going into a kinetic potential energy. So this is my before picture.
So this would essentially be like the minimum energy required,
Yes,
right?
that's it, exactly. So this becomes the minimum threshold energy where this reaction could actually take place. Yep. Okay, so my before picture looks like this. My after picture looks like this. And that's kind of the convention we have in these kind of problems. The convention is, I'm going to look for that minimum amount where we make the momentum add up to 0. So I got two kinetic energies coming in, and then how many potential energies do I have here? How many potential energies do I have between these two nuclei? How many interactions are there? Just one, right? So the potential energy here is going to be given by K, Q1, Q2 over the distance between them. And in this case, Q1 and Q2 are equal to what? Well, I got a couple of carbon nuclei, yeah.
Is it just R? Just R or 2R?
Right now it's going to be R, so I have to be careful about how I define this. The R that I have defined here would be center to center. So that means that I'm going to have to get two of these smaller R's. So I guess I'm going to call this R1, I'll call that R2. And I'll call this K, E squared, times Z1 and Z2, because this is going to be equal to Z times E, where Z is equal to 6, because they're both carbons. Now, if one was carbon and one was helium, how would that change things?
Let's see.
And if one was carbon and one was helium, then one would be 6 and one would be 2, right? But that would complicate things in terms of the center of mass. That would make this part more complicated. Okay, so Z1, Z2, Ke squared divided by R1 plus R2. Now here's a couple of shortcuts we can use. Ke squared is what? That was my 1.44 MeV femtometers. R1 and R2 are going to be equal to what? These are nuclear radiuses. And R1 is going to equal R2. Why is that?
Same.
Because they're both the same, yeah. And then what that's equal to is 1.2 femtometers times A to the 1/3. For carbon-12, what's A going to be equal to? The notation here is terrible. I mean, A doesn't, it's not a good mnemonic at all. A is actually counting what? Total nucleons, which would be 12. So A is going to be equal to 12, and that says R1 is equal to R2, and that is going to be equal to 5.5 femtometers. Well, how much of a separation do we want to reach here? We want to hit 11. So we would like to get the two nuclei so that their centers come within 11 femtometers of each other, and that means their surfaces are just going to come into contact. And you realize the nuclei don't have surfaces, right? I want to be clear, that's just vocabulary that we can talk about. So they're going to be close enough that they come within 11 femtometers, and I can calculate the potential energy from that. That's going to be 1.44 MeV femtometers. Z1 and Z2 are going to be a couple of factors of 6, and then R1 plus R2, yeah, 11 femtometers. And the potential energy that we need for this comes in at 9.43 MeV. How do I calculate the kinetic energies? Divide by 2, right? Just divide by 2. So each one of the kinetic energies, each nucleus comes in with a kinetic energy. Those get combined. So we're going to get kinetic energy of 1 plus kinetic energy of 2 is equal to that potential energy. Okay, so we can just divide through by 2. And that gives 4.71. Okay, and that's all, that's what they wanted, right? It was kinetic energy we were after. Yeah, okay, part C says what temperature would we have to be at so that on average, these nuclei would have this much kinetic energy. Now, that's not really what happens in stars, right? Stars, you're really working off the tails of the distribution in that it's the fastest moving among the group that are undergoing fusion. Most of the nuclei at any particular instant don't have enough kinetic energy. But what we're going to do is we're going to take this number and set it equal to 3 halves kT, where little k is equal to what? Boltzmann's constant. I guess Boltzmann's constant has to be in your notes too, right? And we can solve for the temperature. And the temperature came out to be, I got 3.6 times 10 to the 10th kelvins. That would be 36 gigakelvins, 36 billion kelvins to have enough energy around that these nuclei would just be reacting all the time. That's a really large temperature. Which is why these high mass stars are so amazing, and I'm so thankful for them. Just can't let go. I know I have to let go. Just stay away from that. All right, any questions on that? All right, we are down to problem 57, which is like the last problem of the course. And it says, estimate the radius of a neutron star. Okay. And we're not going to get all the way through this, but we can set a few things up. And I don't expect you on the midterm to go through and derive the radius of a neutron. Let's make that clear first of all. But there's individual parts of the problem that should make sense to you. Come on, how many other courses can you take where your friends say, what'd you guys do in physics today? And you go, well, we calculated the radius of the neutron star. So here's the story with a neutron star. The idea with a neutron star is this. Here's a big star. Fusion shuts down. Who takes over?
Gravity.
So for some number of hundreds of millions or billions of years, gravity has been pulling the star material together. Why hasn't it collapsed? Because of the core, what was happening? Fusion. So fusion reactions in the core have been creating high energy particles, and you've reached an equilibrium. So how can the sun shine for hundreds of millions of years with basically this fixed luminosity? And you go, they hit this equilibrium between the rate of fusion at the core of the sun and the gravitational forces holding everything together. So stars are confined nuclear fusion reactions, right? They're confined by the gravitational effects of what they're made out of. Now, if the fusion shuts down, this effect is gone, and now gravity begins to collapse. And the question is, well, what would stop the collapse? And if we take a look at a star, and if we take all the material in a star and we pack it all together so that it becomes solid-like, we could ask, well, in a solid piece of material, what makes solids not compressible? What is it that when you squeeze on a solid, you can't compress it? Why is that?
Electrons.
It's primarily the electrons. Okay, we saw this back in chapter 39. So what are proton and neutron wave functions like? They're little tiny things. Protons and neutrons, distributions, don't take up much space in materials. The familiar materials around us are limited by compressibility of the electrons. And why can't you compress a bunch of electrons? Yeah, because it's not electromagnetic. It's a quantum effect. The reason you can't compress a bunch of the electrons is because it would force them all into, well, they all have to have their own quantum states. And by compressing the quantum states, the kinetic energies have to go up. I can't confine an electron without boosting its kinetic energy.
So if you, like, because if you did, you'd be like clouding the exclusion gas more?
No, it's just that what happens here is, let's see what happens to energy as a function of radius for this particular star. What happens is we have a gravitational effect. So we have gravitational potential energy. That's one of the important terms here. Gravitational potential energy we can think of as that's what's driving the collapse. As the star collapses, what happens to gravitational potential energy? It goes way negative. Okay. And that means that the star can radiate a bunch of energy away and just keep collapsing gravitationally. Well, there's another effect, and that is the kinetic energy of the electrons. Remember that as this stuff collapses, how do the number of electrons compare with the number of protons? You go, they're the same, right? So there's no real difference in terms of electromagnetic potential energy as you collapse these things. There's a kinetic energy of the electrons, though, that becomes a large repulsive effect. And for most stars, when they collapse, combining these two effects together gives us a curve that looks like this. So we end up with an equilibrium condition. The equilibrium would show up where? The equilibrium would show up at the minimum energy. So we minimize the energy. And it says that at whatever radius or whatever diameter, that's what we're going to predict the star's radius will become. The star's radius is going to become whatever it is that minimizes the energy, because the star just keeps radiating energy away, right? Until it doesn't have anything else to work from. And by the time it's radiated all the energy away, it's down here at the lowest amount of energy it could have. Okay, so that's the idea. That applies for what are called white dwarfs, and it applies for neutron stars. So we'll just get this set. If gravity's taking over here, and we're collapsing everything down, and the electrons are taking up all the space, what might happen as a way to get rid of all those bulky electrons? And the reaction that gets run in a neutron star formation is one that we've been looking at in beta decay. And it looks like this. It says that we take the electrons and turn them into neutrinos. Okay, so during a supernova explosion, the electrons in the core of the star are being converted into neutrinos. Now that reaction can't happen by itself. What would be the other reaction that's happening at the same time? Protons get converted into neutrons. Okay, where have you seen that reaction before? It wasn't beta decay, right? But the N's and P's and E's and U's were all mixed up. What did it look like in beta decay? Well, it was like neutron to proton, electron to neutrino. What did electron capture look like? You go, oh, this actually looks like electron capture. Right, I'm taking a proton, converting it into a neutron. At the same time, I take an electron, convert it into a neutrino. Now, once this reaction starts happening, what happens to the neutrinos? The neutrinos just fly off, right? During a supernova, the star is going to radiate, you know, zillions, I'm sure that means somehow, of neutrinos. Just huge numbers of neutrinos are going to be radiated away from the supernova, and these just take off, right? They're not going to hang around. That means we got rid of those bulky electrons. Once the bulky electrons are gone, what happens to gravitational collapse? It can go a lot farther. And the next thing that it gets stuck with is neutrons, and that's what a neutron star is. So now instead of a bundle of electrons and protons and neutrons, we've taken the protons, converted those into neutrons. We've taken the electrons, converted those into neutrinos, which fly off. So predominantly what's left is a big bundle of neutrons. Kind of like one big nucleus. Okay, and that's what the neutron stars are. All right. So I think we'll stop there. Again, I'll be in the lab room for the next couple of hours. If you guys have questions or just want to stop by and study, that's fine.